Okay. Good afternoon, everyone, and welcome to our webinar. Today, we are very excited about the topic today. I think it will be of great interest to a lot of you. You'll just see me looking to the side every now and then as I admit people from the waiting room. But we'll get started. So just first of all, a few rules and just how we're going to handle things. I just ask that everyone just please keep themselves muted and the video off. It just makes it easier to handle as we go on. And then in terms of the questions, we're basically going to start with Daniel's presentation. And then once we're done with that, we will do a question and answer session. So what I'd like you to do, if you have a question during any point of the webinar, please just pop your question in the chat box. And then when we're done with Daniel's presentation, we will manage the questions. So we'll just ask the questions during that period. And then after that first question and answer session, I will do a quick introduction into ZebraTube and what it is that we do. And we'll do a short question and answer session directly after that as well. Yeah, I just wanted to mention as well that we are recording the session. So if you would like a copy of the recording, you can also just pop your email address in the chat box. You can send me a private message on the chat box, or you can just drop it in the general chat box so that I can send you the recording afterwards. So thank you everyone for joining us here. We have a nice big crowd this afternoon, and yeah, I'm very excited to have Daniel as our speaker today. So just to introduce Daniel and who he is, Daniel is a chemical engineer for Zutari, which a lot of you would know is formerly Oricon in Cape Town, where he has worked as a process engineer in the water and wastewater treatment sector for almost 10 years. He has undertaken postgraduate studies in wastewater treatment with Professor George Ekama at UCT, and currently specializes in the planning and design of municipal water and wastewater treatment processes, including activated sludge systems, anaerobic digestion, rapid gravity sand filtration, membrane filtration, and MBRs, as well as biological oxidation of groundwater minerals. So he is very knowledgeable on a wide range of water treatment topics. He has a whole wealth of experience on projects involving the management and treatment of residues and sludges. So today, in this webinar, he will discuss the implications of different design and operating parameters on sludge generation and how this might influence decisions regarding dewatering technologies. So what I'm going to do is I'm just going to admit some more people from the waiting room, and then I'm going to ask Daniel to start. Just before we do that, for those of you who might not know who I am Karin Spaniolo, and I am the General Manager for ZebraTube here in South Africa. Okay, so I'm just going to stop sharing and then Daniel can kick off.
All right, thanks very much, Karin. And I'm hoping that you'll be able to see my screen now. Can you see it okay? Can I just get confirmation from you that it's broadcasting?
Yes, we can see Dan.
Okay. Great. All right. So good afternoon, everyone. And as Karin has explained, I'm going to talk to you today a bit about municipal wastewater sludge management. This feels a bit weird for me. I am quite used to looking people in the eye when I'm talking to them, and I have no idea how many of you are out there and where you all are and what you all look like, but I hope you're doing well. So I just want to apologize if this presentation feels a little bit like you're sitting back watching TV. Maybe that's nice, but I've been in kind of passive presentations on sludge before, and they can really take the wind right out of your sails. So I'm going to try to keep it a little bit alive, and hopefully I can keep you interested. So Karin's explained a little bit who I am, but I'm really here representing my broader team and our company Oricon, which has now been rebranded as Zutari. So it's a company that's been around for many, many, many years, and has had a big interest in water treatment, wastewater treatment, and sludge management throughout Africa. And we've really a strong team of more than a sort of 100 water technical experts and engineers, and with a big focus on treatment, with over 50 civil, mechanical, process engineers working out of our main design offices, both in Pretoria and in Cape Town here in South Africa. So we do planning, we do analysis, we design, we implement projects, but we don't construct or operate treatment facilities. So we're really in the consulting space. Maybe one day we'll venture that way, but for now we've got a lot on our plate, just keeping up with all the projects out there. So I do recognize some of the names in the audience there, and some of them are my colleagues, which is lovely, but some of them are also people we work with in industry, and for certain you will have collectively more experience and more knowledge than me. So this presentation is going to be less about details and specifics, and it's going to be more trying to frame sludge management within a broader system, and to understand why the headaches that you get in sludge management often have nothing to do with the piece of equipment that you're trying to operate or the chemical that you're trying to dose. They are a result of many, many, many influences that all play off against each other. Okay, these are just some slides that we are trying to publish to make people more familiar with Zutari now as we are evolving, but the main focus is that we're really trying to focus our efforts on the African continent and develop good infrastructure and good systems and good solutions here in Africa. Okay, so to kick off, I think some of you may be familiar with sludge management, some of you may be very familiar, and some of you may have no idea really where it fits into things. So I want to start off by really casting our net as wide as we can and standing back and wondering what on earth is the point of all this, and what are the objectives of wastewater management or wastewater treatment and sludge management. So this is an image I came across which is really quite captivating. Some of you will recognize it as a map of South Africa and parts of Namibia and Botswana, which it is, but it's kind of a route map. It looks like veins and arteries or roots percolating through the soil, and it's exactly how it feels to me, that the rivers that transport water around our lands and our communities, they provide the very life that we need to survive. And if water couldn't move and couldn't reach its destination in a good state, then we could probably say that we wouldn't be able to survive at all. But we don't often give rivers that kind of respect. We sometimes view them more as a way to transport pollution away from us, or to try and keep where we are clean, but if the river can just take everything away, that'll be great. So that's a big concern. If they are really bringing the life to our lands, then how can they do that when they are polluted and degraded? And of course, when they finally reach their destination, they transport all of that pollution downstream and ultimately to the sea and to estuaries. And that obviously has major impacts on marine life. And along the way, some of that water percolates into the ground, into the groundwater and aquifers, and many people rely on those aquifers for water, either for drinking purposes or for irrigation or industry. So we want to, in wastewater treatment, we want to make sure that the water we treat is clean enough that it can be beneficially used in agriculture, in industry, that it supports life downstream, and that even perhaps is clean enough that we can start thinking about reusing it again and again within our own economies. Now, sludge is a bit of a different objective. In wastewater treatment, you're trying to get a nice clean water, which means everything you take out of it is going to report to the sludge, or maybe it's going to evaporate as a gas into the atmosphere. The objectives in sludge management are really to retain as much of that, we'll call it pollution, but as much of those unwanted constituents as possible in the sludge. You don't want to lose them all again to the liquid stream. At the same time, for municipal wastewater, you want to produce a sludge product that is not attractive to disease-carrying vectors like this guy or rats, because it's got to be transported and disposed of safely somewhere, and you want as many of the pathogens and as much of the embodied energy to be depleted, that doesn't encourage vector or doesn't attract vectors. Of course, there's also odors that come with municipal sludge, which are kind of unpleasant. If anybody lives nearby a wastewater treatment work or travels past a wastewater treatment works, you'll know the odors that are associated, and those are mostly from the sludge. If there is embodied energy in the sludge, it can, you do dispose of it in landfills, those bacteria in the landfill might break it down and start releasing methane gas, which can cause fires, can cause spontaneous combustion of a landfill, or it can escape to the atmosphere as methane gas, which is a really significant greenhouse gas. And then, of course, wherever we send the sludge, it's got to be stable enough that it won't leach contaminants and pollutants into the ground or the soil. So those are really what we're after. Now, what is in the sludge is a direct result of what comes down the pipe in the wastewater. So we know that this is, for those of you who haven't been to a wastewater treatment works, municipal wastewater tends to look kind of like this when it comes through. It's been through many pump stations and pipes, and it's been all blended and stirred up so that it kind of looks fairly homogeneous. But you can notice that it's almost entirely water. We know it's water, but what else is it? Okay, anything that gets flushed down a drain comes with it in the wastewater, and that's everything you can think of in your daily activity, but also from restaurants, from industry, soaps, cosmetics, detergents, whatever you can think of comes down. And given that a lot of it is human or animal waste, it brings with it certain microbes, and some of those are not altogether friendly. So that image on the top right is a zoomed in, magnified image of the cholera bacteria, which, as you know, can lead to huge health outbreaks, equally as scary as the one we're currently in. So that's gonna come down with it. So it contains not only water, it also contains what we're calling energy, nutrients, inerts, and pollutants. And the energy is largely bound up in organic molecules, and some of those are biodegradable. They can be easily metabolized by microbes. Some of it is not so easily biodegradable. It's more fibrous. Some of it is particulate and can be removed with physical means, and some of it is soluble, and you need to look at other ways of removing that from the wastewater. The nutrients are macronutrients and micronutrients, so all the things that we eat to make us strong, or that get bound into detergents, whatever isn't used by our bodies and comes out in our excrement, that contains a lot of nutrients, sometimes a lot of protein, a lot of organically bound nitrogen, phosphorus, even sulfur. Then there's some minerals and salts, so those can come down with the wastewater, and those are the three main targets that we're concerned with. So the energy, the organic molecules, whatever we can't remove in the wastewater treatment system will report to a river, and all the bacteria in that river will consume those organic molecules, and in doing so, they will remove oxygen from the water, which will turn those rivers anoxic and lead to sort of fish kills and the death of that riverine ecosystem. similarly, nutrients can act as a food source for algae in the river. And the algae will bloom. You sometimes see that in South African riverways. Or not algae, sometimes different aqueous plants. And when those die and break down and are metabolized by bacteria in the river, then they consume oxygen from the river, and the river turns anoxic, and you get fish kills and destruction of that riverine ecosystem. So energy and nutrients are tied together really, really closely. The minerals and salts, if we're not careful, we might end up causing a higher increase in salinity in our river systems, which obviously is not safe for those ecosystems. And then we look at inert grit and hard plastics and things like that, and pollutants, which include pathogens and sort of chemical toxins. And those might include the more scary things that people are becoming aware of, like hormones or endocrine disruptors or persistent organic pollutants. All right. So that's, now we've got an idea what is our objective and we know what's coming at us. We've got to think about how are we going to treat this. So I'm going to try breeze through this as quickly as I can without just completely bewildering you too much. But hopefully it helps. So this is it. This is as good as we've got around the world in terms of wastewater treatment. We have dirty water coming in from our catchment, from our economy. We've got a couple of treatment steps, and then hopefully we have nice clean water that can go back into the natural environment. Or if it's really clean, maybe we can use it for irrigation on farms. So I'm going to take you through a little bit how each step in this process works and how it's going to impact on sludge generation. So the first step is usually to remove coarse debris, and that can be condoms and tampons and earbuds and grit and bits of rags, and most of this can cause huge impact on the other equipment further downstream. So it's really critical that you can remove as much of this as possible. This is usually considered sort of hazardous material, specifically biohazardous. Okay, the next step is to remove finer particles, and we call that primary treatment. And it's not just about removing particles. By far, the largest amount of pathogens live within the particulate matter of the wastewater. So by removing particles, you're effectively reducing the pathogen load on the wastewater, which is great. And that most typically is done in settling tanks, these very big, often concrete tanks that we just allow the particulate matter to fall by gravity to the bottom of the tank, and you let the clean water go off the top. So what's left? Now you've settled out and screened out all the coarse stuff. You've got, what's left is some fine particulate matter that's suspended. And you've got dissolved material, which is all in the liquid phase. So that gets us to what's called secondary biological treatment. That's probably nearing on 100 years old in its use around the world. And then some solid liquid separation. So the idea in the biological treatment is to use microbes. And this is a great diagram. This is kind of our family tree of the whole known living world. So in the middle, we have the last common ancestor, the last single common ancestor, and we believe that all of these different life forms were descended from them. And we're the green one over here, the Eukaryote. But to give you an idea, almost all of these other classes participate in wastewater treatment, in a biological wastewater treatment process. And as a little example, the proteobacteria there's about 100 groups of proteobacteria, and the gamma proteobacteria consists of this many. So to understand how each one of these microbes behaves is really unhelpful, because we're dealing with a complete consortium of just thousands of different organisms. But a lot of them are really, really good at converting soluble organic material and soluble nutrients into biomass. And they basically are metabolizing food that's in the water and growing. And what's nice about them is that when they grow, they become quite dense and they're very easy to separate out just by settling. But if you feed them food and you leave them for a really, really, really long time, then they start to compete with another class that are less dense and are more kind of filamentous. And these are commonly called filamentous bacteria. And they don't like to settle in a tank, so they're very hard to remove. But ultimately, how the biomass grows dictates how your sludge behaves and how it dewaters. Okay, so this biological treatment is often referred to as activated sludge if it's done in suspension. If it's done on trickling filters, it's called the biofilm process. And the idea is you supply these bugs with as much oxygen as they need to metabolize the food that's in the water. And in doing so, they grow. Some of them are good at converting ammonia so that you don't have so much ammonia in the water. Some of them are good at converting nitrate so that you don't have nitrate in the water. And some of them are good at assimilating dissolved phosphorus into their cell structure, which helps you remove phosphorus from the water. But ultimately, we're just talking about biomass and bacteria. So then the solid liquid separation can happen usually by settling or perhaps by membranes if you have more sophisticated separation technology. So what's left is anything that your membrane can't remove or that doesn't settle in a settling tank. Perhaps some microscopic pathogens like some bacteria, some viruses, some parasites, and any soluble organics and nutrients that are not biodegradable will pass through. And that's where you might have a tertiary treatment step to address those, which could involve more filtration and disinfection. So that's the whole system. But that's not really why we're here today. We're here today to talk about all of the streams that come from those as residuals. So all of them generate streams containing solids. The settleable solids in the raw water we report as primary sludge. Then the biomass that is grown in the biological treatment reports as secondary sludge or waste activated sludge. And then if you have tertiary treatment, you might have backwash wastewater that contains some solids as well. And then the coarse screenings and grit that you remove upfront, we just call grit and screening. So those are, all of these need to be managed appropriately. And while it's helpful to think that this is where the solids are going, those solid liquid separation steps are not very sophisticated. So we're really transporting a hell of a lot of water with those solids. They're still very much in a liquid slurry, at least 95% still water. Now we've got to figure out what do you do with this very liquidy stream where you're trying to isolate the solids. So the first thing we've said is that the pre-treatment is just screening out very coarse debris, and that comes off quite dry, and it's very easy to separate that out and remove it from your treatment process. It probably needs to be disposed of at a hazardous landfill or even incinerated. So the other streams, however, contain so much water that they're not really economical to transport or dispose of. So you need to thicken them up, and that's really what we call thickening. And you can do them in combination, or you can use different technologies depending on which sludge stream you want to concentrate. And that thickening process may make use of gravity separation. So again, just letting dense material to settle down and letting cleaner water to overflow the top. It may use more sophisticated mechanical machinery, like a gravity belt thickener. So as you can see, by dosing a little bit of chemical, you're able to separate the solid and the liquid quite nicely. And then by letting them sit on a perforated or porous screen, this very fine mesh screen, the liquid can pour through quite easily and leaving a nice thick solid on top. There are other technologies as well, like flotation, but we're not going to get too deep into that. I just want to emphasize that some of those thickening processes may require chemical addition. They typically aren't very energy intensive. That comes later. So now you've got this thicker solid stream, which is good, but what happens to all the liquid? Well, that liquid's got to go somewhere. And it's definitely not clean. So typically, we can return that back to the wastewater treatment works, back to the head of the works. All right. Now, the sludge is thick, but it still contains a lot of biodegradable organics. So you've managed to isolate them into the sludge, but if you leave it lying around, there's still plenty of food left in that sludge to attract vectors and flies and everybody. And it also can release quite nasty smelling vapors if it's under anaerobic kind of conditions. So if it's just left in a big pond or left in a big heap, it will turn into quite a stinky situation. So stabilization is a term that refers to how do you reduce the active fraction of the sludge? How do you reduce the amount of food that's available for microbes and for vectors so that it's safe to store it? And those kind of technologies include more aeration. So this is now we're dealing with sludge, and we call it aerobic digestion. So we're digesting the sludge, trying to get the bugs to eat as much of the leftover organic material, as well as their own dead friends, which is a little bit cannibalistic, but apparently that's what they do. We can also stabilize the sludge by mixing it with a bulking agent like wood chips or sawdust, and stacking it in big piles and getting more microbial activity to compost the sludge. So this uses very little energy, but you do need a lot of bulking agent to make sure it doesn't become all wet and anaerobic. You want a lot of air to be able to circulate through those heaps. Then you can consider storing all of that sludge in a heated and well-mixed tank, which is called an anaerobic digester. And under those conditions, you can cultivate a different family of microbes. There are here that are methanogenic bacteria, and they're able to eat some of that leftover food and release it as a methane-rich gas, and that's what we call biogas. So by starving them of oxygen and by keeping them warm and by keeping it nicely mixed, you can effectively stabilize your sludge and recover energy as biogas. So these are the typical types of digesters that we see in South Africa on the older plants. Or if you are less interested in running another process, you can just fill sludge lagoons or sludge ponds. It kind of is functioning a little bit like anaerobic digestion, but it's not heated and it's not well mixed. So we can't be sure that we're getting proper stabilization of the sludge there. Also, once that sludge has been sitting at the bottom of a pond for a long time, it becomes quite difficult to dewater. Also, since some of these ponds are quite old, some of them are not lined, and you're stockpiling sludge and wet sludge, it's a huge volume over the course of a year, that might percolate into the groundwater, and you could be at risk of contaminating the groundwater. So the Department of Environmental Affairs and the Department of Water Affairs has quite strict limitations on whether new plants can be designed with these sludge. They obviously take up a large amount of space as well. Right, now you've got a stable sludge, but it's still got quite a bit of liquid in it. And if you've digested it, we might refer to it now as digestate rather than sludge. And you've got to, if you want to dispose of it more economically, you really can't afford to transport all that embodied water. So to remove all the water, we do a step called dewatering. And this usually relies on the addition of more chemicals, which we call poly. They are polyelectrolytes or polymers, cationic polymers that are able to push and repel the water away from the surface of the solid particles. You might need, so by doing that, the particles can be squeezed closer and closer together, which expels the water in between them. You might need machinery and energy to apply quite strong shear forces to the sludge or the digestate, and those shear forces are able to disrupt the structure of some of those particles and some of that digestate or sludge, and that allows you to remove more water. So these all have to work nicely together. The chemicals, the machinery, and the energy that you apply to it to get a really nice thick solid. But what you want is a solid material that can come out of the dewatering step that is stackable, that is no longer will no longer collapse. And we've gone from about 5% solids out of the thickening step all the way down to, or all the way up, should I say, to around 15 to 30%. Some suppliers will even say higher solids concentration. So globally, there are a few standard technology types that people like to use to do this. They're often technologies that are borrowed from mineral processing sector or from the food and beverage sector that are now finding good application in wastewater treatment and environmental engineering. A decanter centrifuge is a very compact machine that allows you to separate out solids from the liquids very effectively, but it does require quite a lot of energy. It's a rotating bowl that spins at very high speed, and then a screw on the inside that scrapes off the solids as they get stuck to the side of the bowl. It also requires quite a lot of chemical addition, so they can be quite tricky to operate, and they're sensitive to any contamination with grit or sand that weren't properly removed upstream. Other technologies include screw presses, which are a little bit, I would say, less energy intensive. They also still require chemical addition, and that's a rotating screw that squeezes the sludge against the wall of a perforated drum. There are belt filter presses, which allows you to squeeze the sludge between two sheets of a textile belt, and that belt is slightly permeable, and those get squeezed over a number of rollers. So it's kind of like making pastry and rolling two sheets together, but it's done in a machine at quite high forces on those belts, and you should get a nice dryish cake, dewatered sludge that might resemble something like this on the right. And that can be stacked and stored in a silo and then transported away to whoever wants it. So that's the million-rand question, is who wants it? Of course, there's also the liquids that come out of this dewatering process, which are much smaller in volume, but still contain a lot of energy and a lot of nutrients. So depending on what sludge or digestate you're dewatering, those return streams may contain quite a lot of energy and nutrients that the treatment plant has to accommodate. And that has to be handled understanding the dynamic loading on the treatment works. So once you've got a nice stackable dewatered sludge, you can transport it off site, either to a landfill if it's hazardous, or it can be applied to land if it's stable, or it can be incinerated if you are in need of a cheap heating source. So that's what land application can look like. There have been in the past very well drafted and strict guidelines as to what the maximum application rates would be. So how many kilograms of sludge can you apply to a hectare of land, depending on the quality of the sludge. And that quality is measured in terms of how stable it is, how many metals there are in it, and how many parasites there are in that as well. So the there's big controversy around land application around the world. Some countries prohibit it and other countries completely rely on it as a way to retain nutrients on their agricultural sector. But it has to be done carefully so that you are not over nutrifying your soils and that you're not ultimately causing more pollution to the environment. If you've done so well to remove these nutrients from the wastewater at your treatment works, but a farmer applies too much and then it rains and it all washes off into the river anyway, what exactly did you achieve? Okay, so if it's very expensive to transport your sludge or to dewater it, dispose of it or incinerate it, then you might say, all right, the cost is tied still to the volume of material that I'm having to move around. If I could drive off more water from that sludge, then the volumes would come down significantly. So from a 30 to 40% solid cake coming off your dewatering process, maybe you can push that up to 60, 80% solids if it was dried. To get that, you have to apply heat. It's the only way to sort of evaporate off the water, and that heat can either come from the sun in passive solar drying systems. So in South Africa, we have certain parts of the country that are really well suited to this, and down in the Western Cape for sure. Very affordable way of drying sludge. But other places where the precipitation in the year is too high and the humidity is too high, you might not get effective evaporation just by leaving it outside. And there, people consider building these big warehouses or greenhouses and pushing hot air just through fans over the sludge, and they include these little funny cars which drive around and agitate the sludge so that you keep evaporating off the moisture as much as possible. If you don't have the space for that, which many people, or the interest to build a huge greenhouse and then fill it with sludge, you might consider a more compact but a more energy intensive option, which is to import heat, either gas or oil, or even if you have to use electricity, generate enough heat to pass through a kiln and dry the sludge until it's really bone dry. But once you've got this super dry sludge, your options are still limited to putting it on land or landfilling it or incinerating it. Incineration is not something that's considered in South Africa, but in other countries where there's a high demand for space heating or industrial heating applications, they have no problems incinerating that dried sludge. So this is the whole picture. And I think in summary, I'll just rush you through it again. You've got thickening processes that are trying to concentrate up the sludge before you can really deal with it. Those include gravity thickeners, dissolved air flotation. So that's flotation by bubbling air through and hoping that the sludge attaches to the air bubbles, or gravity belts. Then you've got stabilizing processes. You've got two, which are designed to remove the active organics left over in the sludge. You have dewatering processes, which are really intended to squeeze out as much water as you can. And those include centrifuges, belt presses, screw presses, even hydraulic filter presses, and the kind of geotextile sock filters that Zebra Tube is supplying. You've got drying processes, which might be passive using solar energy or might require imported energy. And then you've got really limited options in terms of disposal. So the implications of how the process affects the sludge management are quite obvious if you look at it holistically. You've got this liquid treatment up on the top, and you've got the sludge treatment down on the bottom. Now, the bigger environmental impact is felt when the liquid stream fails. When you have pollution of a river, just the sheer volume of water that is discharged every day from a wastewater treatment facility is so huge that the impacts are felt very radically, whereas the sludge impacts are a little bit more localized. So there's a desire to try and separate the two as much as possible, and segregate them so that they're a little bit independent of each other. But as you can see from this flow diagram, there really are these clinch points where they interact. You've got all the functionality of the liquid stream treatment processes dictates the quality of sludge that the sludge treatment processes receive. And then at the same time, the effectiveness of the sludge treatment processes determines the quality of the return streams, the filtrate streams, the centrate streams, these thin blue and green lines that are returning to the head of the works. So to keep them segregated, you've really got to build in a huge buffer in between the two. And that requires large storage tanks. And storing sludge is not easy because you don't want it to go frot or septic. It requires a large redundancy on machines so that if one goes down, you can still dewater, and those machines are quite expensive. There's more, I think it's probably safe to say that there's more tricky machinery to be operated and maintained in a sludge treatment stream than on a conventional wastewater, on the liquid stream of a conventional wastewater treatment plant. You've got these quite heavy machines that use a lot of energy, as well as very sensitive dosing of chemicals. So we've got a pre-treatment. If we can't remove enough grit and screenings from the pre-treatment, well, then all of that is going to report as primary sludge. And grit and screenings in sludge management are really, really difficult to deal with. You've got the influent wastewater characteristics. So what were all those things that we all flush down the toilet or pour down the drain, or let go down the shower hole every day. And depending on the wastewater, how much of it is organic, how much of it is inorganic, how much of it is particulate, how much of it is biodegradable, that's all going to affect the quality of the sludge that you generate first in the primary treatment step, but also in the biological treatment step. If that wastewater has a lot of heavy greases from soaps or from restaurant waste, all of those things affect the quality of sludge that you're going to try and dewater. So then your liquid stream treatment objectives of making sure that your water that you produce is to the right quality is going to dictate the selection of the treatment process and what type of microbes you are going to grow in your bioreactor. So depending on what type of microbes you grow, that's the excess biomass that you're going to have to remove every day, and that's the sludge which you're going to have to dewater. So different microbes have different dewaterability characteristics once you remove them from the bioreactor. Then it's also operational selections of how long you keep the bacteria in the bioreactor for before you remove some. So that's really how old the sludge is that you, or how old the biomass is that you've cultivated in your biological treatment step. The age of that sludge also impacts on how easily it's dewatered. And then depending on how you operate your solid liquid separation step in your liquid stream wastewater treatment plant, will impact on how thick the sludge is that comes up either your membranes or from your SST, your settling tanks. And that's obviously going to impact on how your thickener performs and how your dewatering performs and your drying step. So it's nice to put a line across here and say we're going to keep one separate from the other, but in practice, it's really not achievable. It's an integrated, complex system. And that's really what makes it so challenging. Okay, what I've presented to you up until now has really been the mainstream of municipal wastewater treatment in my experience, and I believe in our experience as Zutari in Africa and in the Southern Hemisphere more generally. But there are a lot of ideas about how wastewater treatment could change in the future, and they're driven by changing constraints. So as climate change becomes a key driver for decision making, there's the changing economy and access to capital drives things. As cities develop and their availability of land changes, all of these are ultimately going to drive wastewater treatment to respond with innovations and adaptations. And some of these changes that are driven primarily at the wastewater treatment plant for the liquid stream are going to have knock-on effects for sludge management. And they include solutions that consume less energy for treatment, and some of those are plant-based passive systems like the Organica process, which allows bacteria to grow on the roots of plants that are allowed to float in suspension inside of your bioreactor. The plants absorb some of the nutrients, and their root structure is so fine that it acts as a perfect housing medium for bacterial growth. There are high-tech aeration options that concentrate a lot more oxygen into your bioreactor. There are designs that aim to produce a biological sludge that is very granular in nature and very dense and can settle very easily. There are high-tech dewatering options that use very sophisticated and heavy energy-intensive machinery to change the structure of the sludge. That includes thermal hydrolysis, and then other processes that use microwaves or electrical fields to dewater the sludge directly. Some of those are still in development, but others are already reaching maturity. Then there's a focus on selecting designer organisms or designer families of organisms to target particular wastewater constituents. So the Anammox bacteria or Anammox process targets is a very specific bacteria for removing particular constituents, and that is going to have a different behavior when it comes to dewatering and sludge handling. And then there's the shift in paradigm of saying, well, our objectives here, are they just about protecting the environment and reducing our impact? Or are we in a state of resource scarcity and we need to look at these sludge streams and the liquid streams as valuable resources? Can we recover the water for reuse in irrigation, in industry, in the commercial sector, or even at a municipal potable water scale? Can we use targeted treatment processes in our sludge handling plant to recover as much energy as we could, either as biogas or biomethane, or even combusting those dried sludges? Can we use specific process conditions or technologies to recover targeted nutrients from that sludge, like ammonia and phosphorus? So there's a kind of interest in that, and those will shift how we use dewatering equipment and how we will structure our dewatering designs. I can't seem to find a clock anyway, so I don't know how long I've been babbling on, but we're getting there. And then there's also the whole question around, well, why is all of this stuff ending up in the water in the first place? Are there not alternatives to handling our human waste, our food waste, our cleaning, our household cleaning, industrial cleaning that doesn't require so much water, so that we don't pollute so much water? So these are just a few images to give you an idea of what I'm talking about. This is the Murray and Roberts' Organica demonstration plant in the top left and bottom left at Verulam in Durban. These are dry composting toilets that don't rely on water, but which are, allow you to compost your human waste in situ right underneath the toilet. This is a thermal hydrolysis plant which cooks sludge at very high temperatures and under pressure, completely disrupting the cell structure of the particulate organics and allowing them to both be digested and stabilized more easily, but also ultimately dewatered far easier. So these, perhaps instead of having a liquid return stream from our dewatering process that's full of nutrients, perhaps we can look at some of those processes to recover nutrients as a valuable resource. And in stabilization, if we are going to generate a methane-rich gas, perhaps we can clean it, concentrate it, and use it to generate power or transport fuels or industrial heat as needed. And then obviously, if we've gone through all this effort to treat water to make it clean, and then just returning it to the river, perhaps we could be looking at ways to purify that even further to a state where it's usable back in our economy. Okay, so I've got a bit of an unconclusion. I can't really conclude very much about sludge management. I think it's one of those things that nobody likes to think about. And when you start thinking about it, you find that it's both very difficult and very fascinating. So if we go back all the way to our objectives were to try and mitigate against environmental burden through releasing nutrients back into the environment after we've worked so hard to remove them from the water. We're trying to stabilize sludge to prevent vectors and spreading of disease and reduce odors. And ultimately, we might say we have bolder objectives and we want to look at recovering resources where we can. But the questions that will always be asked is, where's the priority? If you are trying to design, or whether you're trying to plan, or whether you're trying to operate a wastewater treatment facility and a sludge handling facility, the priority of what those two have to do together is ultimately going to drive how you select equipment, how you operate the system. If you are discharging treated water into a very sensitive environment, you're going to have a very big focus on using liquid stream treatment processes that can remove as much as they can from the water. Even more so if we're looking at recovering that water for reuse in the economy. Whereas there might be other applications where the receiving environment is not as sensitive and a simpler liquid stream process might be selected. And that would have huge impact on how the sludge handling would work. The extent to which you can segregate the liquid and sludge treatment processes is always going to be a tough decision, because it feels like spending money on buffers which don't do anything. They're just holding sludge for a couple of days, and they, depending on the size of the plant, those can be huge tanks. Can you afford redundancy on machines if you want to make sure that there's no limitation to your liquid treatment, even if your sludge treatment goes down? You've got enough backup belt presses and backup dewatering systems. So the big decision drivers may be anything. They could be the physical conditions, the climate. They could be the cost of energy. They could be how willing you are to operate complex machinery and chemical dosing. And do you have the interest to do that as an operator, or the capacity to do it? It might be that you're in an area where sand is blowing off the sand dunes next to you, and that's going to ultimately dictate your dewatering, your sludge handling management, because a lot of these dewatering technologies are super sensitive to sand and abrasives. It might be the footprint. You might be in a really densely occupied urban environment, or you might have lots of space next door that you can lay out solar drying beds. And then I think the biggest question is, what is the context? And this is a highly technological field with a lot of impressive innovations in machinery and design. But what is the context that it's being applied to? Can we just import these technologies and hope that they will work for our applications? Or can we adapt them? Can we simplify them down? Or can we actually consider a completely different kind of approach that doesn't rely on sophisticated technology, but maybe relies on other assets that we have, like our climate? And then the big problem is that given the complex environmental hazards associated with sludge, there's always going to be a trade-off there against the economic burden of investing in such expensive equipment. So as a planner or as a municipal authority, to ask the question, can we really afford to spend money on sludge handling when there are so many other basic needs that we need money for? And I think in South Africa's current financial state and our credibility for loaning money, this is going to really be a big driver in how we develop the wastewater sector. Will we actually have access to capital to invest in sophisticated treatment? At the same time, the knock-on effects of environmental damage on economic on the economy are so profound that we have to ask ourselves the same question: can we afford to spend money on this? And then, can we afford not to? Or are those risks just really, really too high? So that's pretty much all I have to say in this presentation. I really have no idea how long I've been talking for. But just to bring it back, that I think if we view our opportunities here, we shape the way and our relationship with water and waste and nutrients and energy, then we can really return, or hopefully we can drive things in a way that aims to treasure our rivers and our soil, because they really are what our lives depend on. So thank you very much for listening, and I'm really excited to get some interaction now, because it's felt very lonely up here.
Great, thank you, Daniel. Yeah, it was, what a great overview. And I don't think anyone has ever given me such a good, very kind of high-level snapshot of what goes on in terms of residue on wastewater treatment works. So thank you for that. So we'll jump into questions. I'm going into the chat box. Okay. Right. So we have a question here from Brian, although I see it's already been answered in the chat box. So I think we'll maybe skip that one. Thank you for answering that. Then Gary asks, what is deemed expensive in terms of disposal costs, like on a rand per ton basis?
I think that's a very good question. I didn't prepare any comparative figures on the transport and disposal costs of sludge management. Unfortunately, there's not the classification of sludge as to whether it is hazardous and needs to be disposed of as a hazardous landfill or not. Used to be endorsed. The guidelines used to be endorsed by the Department of Water Affairs. And my understanding, and I may be a bit outdated now, is that in the last couple of years, those guidelines lapsed, and new guidelines were under review but have not yet been endorsed, which means that the regulation on and guidelines on handling municipal sludge is completely regulated by the Environmental Management Act, which views it as a waste stream and not so much as a resource of value or a compost stream or a soil amendment. And where you fall in between there obviously dictates what kind of landfill you need to dispose at, and by far and away that shapes how much the costs are. I've got a number in my mind of, I'll be wrong if I say it. So what I can say is that in evaluating planning for the City of Cape Town's, some of the City of Cape Town's recent wastewater treatment plants, and looking into the future, the cost of disposal of waste ended up having a major impact on the selection of sludge handling equipment. And the city is trying to drive things in a way that looks to digest sludge and to dewater it as densely as possible for that reason. So even considering different liquid stream implications, the amount of energy that could be recovered, the costs of capital of very expensive equipment. In the end, the biggest driver that shaped the decision one way or the other was exactly what Gary is referring to. Is if you can beneficially reduce the volume and make your sludge more stable, your disposal costs can actually dictate that's a beneficial thing to invest in. And then the energy that you get from biogas or the nutrient value is bonus.
Okay, thank you for that. And then I see Salvin says the centralized concept of wastewater treatment plants is leading to a large emphasis on interconnecting infrastructure and single points of failure. Are the future designs looking at treatment closer to the source?
I can't speak from a municipal perspective. Our community that we're connected with in the research space are definitely looking at that. So decentralized wastewater treatment, particularly as cities in South Africa tend to do, we sprawl, and to service far outlying communities with sewer connections to a central wastewater treatment work is really impractical and unaffordable. So I know eThekwini municipality did a lot of research in looking at different decentralized treatment options and even some dry sanitation options. And I think they found real promise there. So I think that one is going to end up being more of a political question than a technical one, or even an economic one, as the notion of a sewered toilet connected to basic service supply is still viewed by most South Africans as the desired state. And the departure from that is going to require quite a lot of shaping of opinions and perspectives and perceptions. But from the technical side, I think it's all happening in that space. From Bill Gates, who wants to build like R1 billion toilet, down to the much more simple systems that rely on kind of dry sanitation and adding value to urine that you can divert from your waste stream. If you separate urine from your feces, then your fecal matter treatment becomes a lot simpler.
Okay, cool. Thank you. This might be not a quick one to answer, but Lavani asks, what is electro dewatering?
I don't know. I really don't know. I was reading this paper on kind of a review of the dewatering technologies in as a global outlook. So I don't think it's something that has been implemented yet. I think it's still very much in research. I can share that paper with that person.
Yeah, maybe you can send me the paper. I'll send it to Lavani.
Okay.
And anyone else who's maybe interested.
Microwaves seem to be a little bit further ahead. I don't know if you want to do experiments in your own kitchen, you're welcome. But
okay.
Not use the microwave again.
Okay, so Salvin is asking any comments on how digital technologies such as data analytics and artificial intelligence will impact new wastewater treatment works.
Sorry, could you just ask that again?
Yeah, just scrolling back up. So it's just, do you have any comments on new digital technologies such as data analytics and artificial intelligence and how it will impact new wastewater treatment works?
Yeah, so this is something that Zutari, but I mean globally around the world, there's obviously a huge interest in big data and analytics and presenting information in a way that is more useful, as well as predicting where certain behaviors are going to, or certain events might happen to protect your industrial processes. And wastewater treatment is no different. It's a dynamic process that is vulnerable to changes in whatever is coming down the sewer. And there's it's now being kind of promoted and hopefully trialed in some of our newer projects, where by monitoring different process parameters, on the bigger projects, we've got everything is being measured online anyway. So you've got a lot of information coming in. And sometimes, despite all of our experience and our qualifications and our sitting around arguing about these things, we can't pick up the patterns. And data analytics offers that opportunity to pick things up. And what it can result in is obviously saving on chemicals. It could result in saving on energy. It could look at predicting when spikes are going to occur due to historical patterns, and that can warn the treatment work so that they adapt their operations to prevent overflows or to prevent failing to meet their effluent quality. So I think it's going to have a big impact on,
no, I agree with you.
On how we design and operate works in the future.
Yeah. Okay, and then Peter is asking, where do you see the low-hanging fruit in terms of resource or energy recovery?
Yeah, it's a good question. I think I'm glad you asked that question. Wastewater treatment works in a city looks like a huge amount of resources because there are just, megaliters and megaliters of water, and there's tons and tons of sludge. But our bodies are not terrible at converting food into the energy and nutrients that we need. So what is released in our excrement, if you consider that a wastewater treatment works like the one we're currently supervising the construction of in Cape Town, services around 750,000 to perhaps 1 million people. That's a massive number of people. If you look at it on a per capita basis, the nutrients and energy that are recoverable there are not that high. And if you compare it to the amount of energy that we use in our daily life to drive a vehicle, to operate a computer, to charge a cell phone, it starts to change the way you look at things a bit. So the low-hanging fruits are perhaps, before we look at energy recovery, is to look at adopting processes that offset the amount of energy that the wastewater treatment works needs in the first place. If a wastewater treatment works is receiving purely domestic municipal wastewater, it's unlikely that it will ever be able to produce more energy than it needs to treat that wastewater. I don't know of a single plant in the world that is capable of doing that. If the treatment works is able to receive other waste streams, like perhaps food waste or industrial waste, then it's importing energy, but it can recover energy. But just changing the process from a raw water treatment process to a settled process. So some treatment processes don't have primary treatment. They go straight into the biological treatment. By including primary treatment, you can reduce your total energy consumption in the overall plant by easily around sort of more than 20%. And that's a function of how much organics you can remove as primary sludge and then deal with separately compared to what you feed to the bioreactor, where you're pumping energy in by aerating the mixed liquor. So there's opportunities there that I think are low-hanging fruit before we get to energy recovery, which is a little bit technologically more challenging, and it's always going to be limited because you're trying to get energy out of something rather than avoiding putting energy into something in the first place. But just to give you a quick run through, we did a nice study here in the Western Cape for the Swartland municipality that looked exactly at this. And the low-hanging fruits are adopting primary settling to move from surface aeration to fine bubble diffused aeration, to look at composting of sludge. And then there were a few other minor things that could be done. But those were, and then ultimately looking at energy recovery. So you can do those three things long before you look at energy recovery.
No, that makes a lot of sense. Thanks. Okay, I see Gary says he understands that disposal to hazardous landfill is around 1,200 rands per ton.
Okay, he answered his own question.
Yeah.
I think I might know who Gary is.
Yeah, he just says, is this consistent? But I mean, yeah, you might not have a figure, but yeah. It could. I think that sounds right to me. Yeah. Okay, and then Rudy says, regarding the Cape Town sludge study you spoke of, what is the recommended sludge disposal method, especially considering the ban on organics to landfill that is coming?
Okay, I don't want to speak on behalf of the city. They may have someone.
Yeah, don't say things you're not allowed to say.
who's present. At the time of the study, Rudy, we were considering the fate of sludge from the Zandvliet Wastewater Treatment Works, which is the one currently under construction. And that sludge had license for land application in Durbanville. And that was a distance of around 60 kilometers it had to travel across the city. So that was onto fallow farming lands, and it was a good quality sludge that met the guidelines for application to that field. We then looked at other scenarios where that sludge would have had to have been landfilled at Vissershoek. And that obviously changes the game. For many applications, it's not just the disposal cost, but it's the transporting cost to get it there. If you don't have a landfill facility nearby, you might be trucking sludge across a huge distance. So if your treatment process is good in the liquid stream, and if your sludge handling process is good, and it includes stabilization, and you only receive domestic residential wastewater at your wastewater treatment works, there's no reason why you shouldn't be able to produce a sludge that is the top classification, which is called A1A. And that sludge is, according to the old guidelines, which I say now are no longer endorsed, was approved for unrestricted application. So you could sprinkle it on your sports field, you could sprinkle it in your home garden, you could sprinkle it on farms as much as you wanted. As the quality of the sludge that you generate gets worse, that no longer becomes possible. And at some point, you may be causing more environmental damage by applying it to farmland than by putting it in a landfill, unfortunately. So the real goal is not to try to find ways to send the sludge somewhere beneficial. Real goal is to go back and look at what are we pouring down the drain in the first place, because it's there that we compromise the quality of the sludge.
Okay, no, cool. I think that's good. Thanks, Daniel. That I think is all of the questions. I wanted to ask you a question because, yeah, I think a lot of the wastewater works obviously historically has sludge lagoons. A large portion, correct me if I'm wrong, a large portion of our historic wastewater works in South Africa has sludge lagoons, right?
For sure.
Yeah, but there's a movement away from that.
Yeah, I think Do you have a question you want to ask on top of that? Or?
No, I just kind of wanted to understand if that's a correct statement.
Yeah. So I understand that there's a big question mark around sludge lagoons, and they help the operator because it's a very effective way of segregating the liquid from the solid streams treatment. If you can pump your sludge into a lagoon, there's no return flows as much as you have to worry about, and there's not so much equipment that could go wrong or that's available. But it just requires a huge amount of space, and it poses these environmental risks. So as our cities develop, and in the urban context, this is a classic pattern. Wastewater treatment works are designed on the outskirts of towns, and then those towns grow, and the wastewater treatment works is now slap bang in the middle of the town. So then we build another wastewater treatment works further away, and then the town grows, and then that one becomes surrounded by a developed urban area. And the pressures on it on that land become quite apparent, and the pressures of odors and public perception around odors become quite stringent. And I think those are two of the main drivers. There's probably comments that are going to come flying at me, but there's others as well. It's going to make it hard for a municipality to design a new wastewater treatment works and install sludge lagoons, particularly a major metro. I think smaller municipalities, they may be forced to because they're just not equipped to operate a dewatering facility. And I think this is the question, is there something in between? And it's probably an opportunity for yourselves and for others to come up with solutions that are the right application. And I think that like a geotextile filtration system or drying beds or any of these seemingly low-tech options, they have an application there. I think in the big metros, there's just not the land available for passive drying. There's too much pressure to concentrate things up. Okay,
right, we've gone a little bit over time, but I see there's some people who are still holding on, so thank you for that. I quickly wanted to show everyone just a quick video and then one slide on ZebraTube before we log off. I just wanted to remind everyone to, if you want a copy of the recording, please just put your email address in the chat box. So I'm just going to share this. Okay, and just
Are you faced with sediment buildup in dams or liquid waste streams that are difficult to dispose of? ZebraTube's engineered geotextile bags offer fast, flexible, efficient, and cost-effective dewatering solutions. Applications can include dewatering of food and beverage and industrial waste, to dredging and containment of sewage, silt, and natural resources. Small-scale projects can be dewatered using our unique, easily handled 1 to 5 ton bags. Larger projects make use of our tubular bags. In certain applications, flocculant can be added to agglomerate solids to enable efficient settling. Once dewatered, the contained material is dry enough to be easily disposed of or reused. In addition, the filtrate can be collected for reuse. Contact ZebraTube now for your custom-made solution.
Right, so yeah, that's just to give you guys just a quick brief overview about ZebraTube and our geotextile dewatering solutions. And I thought I would just quickly mention a few applications that we do have in water and wastewater. One of our, or I'd say the number one application that we see specifically in South Africa is in the pond or sludge lagoon dredging and desludging. So we do a lot of this refurbishment and maintenance work on historic plants, where a dredging contractor would then typically utilize our dewatering bags to contain the material that is in those sludge lagoons. So this over here is what you would see, and the nice thing about the geotextile tube is they are stackable, which is what I'll show you quickly on the next slide, and it's a very efficient way, cost-effective and efficient way of dewatering, specifically in the context of dredging and refurbishing sludge lagoons. We've also done a bit of continuous dewatering where the dewatering tube is placed on an existing sludge drying bed, which then means you can get a little bit more sludge containment on that existing sludge drying bed. And it does work particularly well on wastewater treatment plants where they need, like Daniel says, a little bit of a lower tech solution and something that is cost effective and quick in terms of dewatering. Something else that we do often is small scale wastewater treatment work, so kind of decentralized decentralized wastewater work, something that's maybe not a big municipal wastewater work. We do these smaller bags, which you would have also seen on the video, which enables really easy handling of the dewatered material. So the dewatered material can then be placed on a truck very easily and then disposed. So that's just another example. It's a little bit outside of the context of what we spoke about today, but just to mention that. And then I just wanted to just highlight specifically the dredging and desludging. So this is just an example of where the tubes are stacked. So you can really maximize the efficiency of the laydown area. And then this here is just a picture of once that dewatering has been completed and you've stacked up all of your bags and you've had some passive dewatering time, then you would break open the bag and it would that material would be dry enough to then be handled and retrieved. This is just a specific project that we've done in South Africa. It's one of the largest projects that we've ever done. It was 40,000 cubic meters total dredged volume. And there was at some point also a large number of bags that were stacked on top of each other. So that is just my 5 minutes of what is ZebraTube. I don't know if anyone has any questions regarding ZebraTube. Doesn't look like it, but otherwise, I would just like to thank Daniel for his time. I think it was incredibly informative, such good content, and looking at the chat box, I see everyone really enjoyed it. Keep a lookout on both the ZebraTube Facebook page and our LinkedIn page if you want to see more webinars. This is the second webinar in a series that we've done. We've done the first webinar was on mine water related sludge and the sludge management underground, but also on surface. So if you're interested in having a look at that, that is on our Facebook page from a few months back, and we will also be doing some more webinars. So please have a look out for that. So thank you very much, Daniel, and thank you everyone for staying so long.